Alrighty, welcome to lecture 13 of topic 2 of unit 4, wave particle duality. This video will be covering the main ideas of chapter 12.3 of book 2 and a little bit of chapter 11.6 also of book 2. Please complete this reading before class. Here are your learning, intention and success criteria. Please have a read over and attempt to complete the KS table down the bottom right. Okay, so looking here we can see that we're after you being able to describe this thing called wave-particle duality and identify evidence. That's the direct descriptor out of the syllabus, so we need to be able to do those two things, and I've just broken that up into success criteria there for you. In terms of your knowledge, you've got to know, well, what is wave-particle duality? If you don't know what it is, it's pretty hard to describe it. And then the other bits of knowledge are you identify what are these evidence for the wave nature, what is the evidence for the particle nature. Now, just a bit of word on language here. The syllabus uses the word wave characteristics and particle characteristics. A lot of the text and maybe some of the questions we'll see on the exam may use wave nature and particle nature. In this case, they mean the same thing. So, let's talk about the wave model. In our videos about waves in Unit 3, Topic 3, and then when we talked about Young's experiment in Unit 4, Topic 2, we've examined light as a wave model. So all the properties known that could be explained using Huygens' model, so reflection, refraction, total internal reflection, dispersion, diffraction, and interference, that all basically consolidated everything into the idea that, yeah, light's probably a wave. Maxwell came along in the 1850s, he did his work on electromagnetic radiation, and then everyone was like, yep, light is a wave, we can put away light as a particle in the graveyard of old scientific ideas. Of course, Einstein came along. Einstein came along and basically determined or showed that a spread out wave could not interact with an electron. Okay, so a wave is where the energy is spread out, but that could not interact with an electron and cause it to do these things that they were observing. So without this, we couldn't have photoelectric effect and we could not have atomic spectra. And so Einstein said, no, light's got to be a particle. Okay, can't be a wave, it has to be a particle. So we've got two problems here. Young's experiment and all these other physical phenomena pretty conclusively said light's a wave. Einstein came along, and I've shown you that video in class, and said, no, listen to me, light is a particle. And so Einstein resolved this with the proposition that it was both. So Einstein proposed wave-particle duality as a way of resolving it. And the idea was that light acted as both a particle or a wave, depending on how it was being observed. If you observe it directly, it acts more like a particle. If you observe it indirectly or after the effect, it acts more like a wave. So here's the definition that you should use. Every particle or quantum entity may be partly described in terms not only of particles, but also of waves. And this term quantum entity sounds all fancy and scary sounding. It basically just means anything small. Right? Anything that's small has both wave and particle nature. All you care about at this point is light, so photons of light, and electrons. They're the only things that matter for you. Quarks, that's next year's problem. Gluons, next year's problem. And the stuff on quantum next year can't refer back to those because it's not part of Unit 4 or Unit 2 for the Year 12s next year. So, what you need to know is that light and electrons, both of these do particle and wave behavior. This image is one that was taken in 2015 when I first started teaching, incidentally, and shows light as both a wave, this section here at the top, and as a particle, this little bit here down the bottom. And they were saying the scientists who took this image said it captured quantum duality for the first time. But yeah, that's just an interesting side point. So let's start talking about some of the evidence for this. Compton scattering was one of the biggest ones here, and it showed light had particle behavior. Now in this image, we have here light, okay, in this case an X-ray. X-ray is just fancy light hitting some graphite, carbon, and then measuring the scattered rays. So rays that didn't hit anything, just went straight through, very similar to Rutherford's experiment with the gold that we've talked about previously. And light light that did interact with the graphite scattered off over here to interact with another receiver. But the electrons would scatter off at an angle as well. Okay? And here we have the incident light coming in, interacting with an electron. The electron would be ejected, and the outgoing ray, the refracted ray, would be coming out here, and it would have a different frequency. Okay, so there's some important points to keep in mind. The photoelectrons, they're getting ejected at an angle complementary to the angle of the scattered light. Think of it like if you're playing billiards, you hit your white ball onto a coloured ball at an angle, the white ball will bounce off, and then the coloured ball will bounce off at a different angle to it, but they go away from the same central point. And the change of frequency is also really important here, because remember, frequency is proportional to energy. So if there's a change in frequency, there must be a change in energy. And it was equivalent to the kinetic energy of the electron. So the change in energy, the change in light energy of the photon became the change in kinetic energy of the electron, and so that showed light had momentum. And so if light has momentum, well, that's a particle thing. De Broglie came along. Note, if you're writing his name and it's not a cat at the start of a sentence, the D should be lowercase. De Broglie came along, used Compton's work, and developed an equation to relate the momentum of the photon with a wavelength. Pretty straightforward. So the wavelength here in meters, the momentum of light in kilogram meters per second. Now, if you're dealing with light, that's where you stop. You don't worry about thinking about mass of light. We know its velocity would be the speed of light, and h just being Planck's constant. But that's all you need for the momentum of light. So let's have an example for this. Alright, so a source of green light has a frequency of 560 terahertz. Remember that conversion for terahertz, T equaling 10 to the power of 2, is in your formula, your formula document, your formula booklet on your exam. Two things: it wants us to calculate the momentum, and B, determine the speed of a photon. Alrighty. If you're following along, this is on 321 of your textbook. It's in chapter 11.6. They talk about Compton scattering. Alright, so let's go through here. We want to know the momentum, so P equals, I don't know. We are told that the frequency, F, equals 560 terahertz. Remember, convert that to your powers before you even do anything with it. And the formula we've just seen is that lambda equals h over p. If we rearrange that, we get p equals h over lambda. Oops, not frequency, lambda. But we don't have lambda, but we do have frequency. Remember, we've talked about this in class. If you have energy, you have frequency, you have wavelength. They are three facets of the same thing. So connect them. Lambda equals, let's see, V equals F lambda. So lambda will equal V divided by F. Let's substitute that in. P equals H over V divided by F. So P will equal HF over V. Hey, look, it's energy just divided by velocity. Fancy that. And now we can sub that in. Well, what's our V going to be? It's kind of weird. In this case, they've asked us to determine the speed of a photon as the second part of the question. But remember, it's just light. And what's the speed of light? The speed of light is 3 times 10 to the 8. So P will equal 6.626 times 10 to the negative, what's the power on that, 34, times our frequency, 560 times 10 to the 12, all divided by 3 times 10 to the 8, and that would be our answer to part B, and we're not going to bother solving that, to give us a final momentum of 0.2 times 10 to the negative 27 kilogram meters per second. Don't forget your units. Very, very small number, but it is, remember, only a single packet of light. And one of the interesting things about this is that you can use, they've got the idea that perhaps they can use this to sail basically spaceships between stars by using the light coming off the sun to hit a sail and propel it along by collisions of momentum. All right, so De Broglie, though, took this idea and went an extra step. He proposed that since light could behave as a particle, perhaps particles could behave as waves. The answer is yes. And this helped resolve that first postulate for Bohr's atomic model that we looked at in the last video. Physicists repeated Young's experiment, remember the double slit experiment, with electrons instead of using light, and found electrons do indeed have a wave-like nature. They observed an interference pattern. So when they shot a stream of electrons through, they didn't see just two bands of electrons hitting the receiver screen. They saw it spread out, creating an interference pattern. They then went and tested it with only one electron at a time. So shooting one electron, letting it be received, shooting another electron, letting it be received, and they found the same thing happened. I've spoken with you in previous years and in this year, the whole idea of imagine walking through two doors at once and high-fiving yourself on the other side. This is what an electron basically does. It interferes with itself by going through both holes at the same time, and we end up seeing an interference pattern. Okay, so we had Young's double split. So let's have a look at the formula again. I've got exactly the same formula here, but instead of saying the wavelength of light and the momentum of light, I've replaced these with wavelength of quantum entity and momentum of the quantum entity. Remember, a quantum entity could be light or an electron. It doesn't change anything else, but now instead of us just going, yeah, it's about light, it's about very, very, very small things. So small things have a wavelength when they're moving. As a note, you all learnt how to calculate momentum last year for a solid object. Mostly we did it with cars and carts and stuff. P for momentum equals mass times velocity. The mass will still be in kilograms. The velocity still needs to be in meters per second. That formula is in your formula booklet, but it's under the Unit 2 stuff. So linear motion. It won't be in the P for under electrical circuits or under heat. That P there will be for power, so do be aware of that. So let's have a look at another example on that. So this is from chapter 12.3. Let's have a quick look there. An electron, we're given a mass this time, has a velocity of 6 times 10 to the 5. Pretty fast, but not super huge. Calculate its momentum, and then determine the wavelength. So we're just going to reverse what we did before in the last example. And then I've got another example. This one's not from the textbook. I went and looked up baseball last night. So the wavelength of a baseball, we're going to work that out. The mass is 0.149 kilograms, so about 149 grams. And the velocity was about 169 kilometers per hour, so I rounded it down a little bit and went to 45 meters per second. And we're going to work out, well, what's the wavelength of a baseball being thrown in Major League Baseball? Okay, so let's start off with our first one, so 12.3. We have an electron, mass equals 9.11 times 10 to the negative 31. Remember, this is a constant. It will be given to you in your formula booklet, so they won't necessarily tell you the mass of the object, but if they told you it's an electron, go look its properties up. It's in the formula booklet. We need the momentum. Momentum is pretty easy. P equals mv. 9.11 times 10 to the negative 31 times 6 times 10 to the 5, and we're going to get an answer of 5.47 times 10 to the negative 25. Don't forget units. Let's have a look at back on this previous question. Here, horrible looking P, I almost couldn't see it there, was 0.2 times 10 to the negative 27, so that's 2 times 10 to the negative 28, while here it's 5 times 10 to the negative 25. So this is over 1,000 times bigger than the other one. Yeah, it's an electron that's moving very, very fast, but it's got a lot more momentum compared to the compared to the photon. But remember, the wavelength is proportional to the inverse of the momentum. So this momentum is 1,000 times bigger. That means the wavelength is going to be 1,000 times smaller than before. Okay, and this is with an electron, so we're going to see some pretty small values here. Let's do our substitution for that. That was part A, that was part B. 6.626 times 10 to the negative 34 divided by 5.47 times 10 to the negative 25 is going to give us 1.21 times 10 to the negative 9 meters. Okay, that's about 121 nanometers. Remember, visible light, the lower end of visible light is about 400 to 380 nanometers. So the wavelength for this compared to light is in the ultraviolet radiation. Okay? So this was a fairly important thing for de Broglie to propose, and of course he got a Nobel Prize for it. Let's have a look at example 2 that I proposed there. The mass of a baseball is 0.149. The velocity is 45. So the momentum, 1.49 times 45. Grabs the calculator. 0.149 times 45 is 6.705 kilogram meters per second. Lambda equals h over p. 6.626 times 10 to the negative 34 over 6.705. 6.626 10 to the negative 34 divided by that gives me a wavelength 9.8 times 10 to the negative 35 meters. That wavelength is so small that it's basically irrelevant. You wouldn't notice it. In fact, that actually might be smaller than the Planck length, so pretty close to anyway. So this wavelength is irrelevant for a baseball that is being thrown at major league speeds. Cars with velocities of closer to 30 or so meters per second, yeah, that'd be about right, go with a mass of over a ton, they're going to have significantly bigger momentums, and so their wavelength, their de Broglie wavelength, is going to be worthless. Okay, so you can work it out for anything at the macro scale, but it has basically no meaning, or at least no meaning at the moment. It didn't have any meaning when I first heard about this when I was your age, and I'm still yet to hear of any sort of significant importance for this. But it does matter for very small things. And the reason I said that this was important was for Bohr's atomic model, so we've got to go back to that. Remember, I told you the 3 postulates. We figured out why of the second 2, postulate 2 and postulate 3, but I said for postulate 1, it was just something that Bohr assumed to be true to make the rest of it work. He didn't have any proof for it. De Broglie's wavelength is the proof. So the wavelength of an electron allowed that model to be explained. With a fixed wavelength, an electron could create a standing wave because the wavelength here will be going, or some multiple of the wavelength, will be going around the atom. Okay? Remember, resonance systems where you have a standing wave are highly efficient. They do not lose energy very quickly. Okay? Remember, Rutherford's proposal about orbital models and circling electrons meant that it should be giving off energy very, very quickly. By showing that the electron was also a wave, the electron didn't actually have to move around it, it just had to have a standing wave in that area, and so that standing wave didn't give off energy. The formula that connects those two things, the de Broglie wavelength to the orbital radius, is also provided to you, and you're expected to recognize it from the text. This is the last one of these N formulas. So we have lambda, that's just the wavelength. In this case, it's the electron. So we're just going to do it in terms of orbiting electrons. 2 pi for a constant, r for the orbital radius. If we go back to our picture there, the orbital radius will be the distance from the nucleus up to whatever radius you're talking about. And n will be an integer multiple. Remember, it has to, because it's a quantum system, it has to be an integer multiple. So it's going to be 1, 2, 3, etc., whatever it wants to be. We could have it all the way up to 100, but you can't have anything less than a 1. So, last example for this one. determine the three longest wavelengths of an electron in a helium atom for which the orbital radius is given as 0.310 times 10 to the negative 10 meters, or 3.1 times 10 to the negative 11 if we wanted to make it a number bigger than 1. This is on page 342. All right, so again, this is about the most complicated thing you can do with this formula. Realistically, you should be using it to explain why de Broglie wavelengths are important for what's what I'm looking for, the orbital structure of an atom, in terms of going, well, this explains the first postulate, this is the formula that actually explains it, rather than it just being an assumed true. So making sure you recognize what these formulas are for. Let's rearrange this because we want wavelengths 2 pi r over n, and we're going to use n equals 1, 2, and 3 because the question asks for what are the three longest wavelengths. If we divide by 1, that would be the longest number, divide by 2, that would be the next biggest, divide by 3, that would be the next biggest. We're told the radius equals 0.310 times 10 to the negative 10, and we'll just substitute those in. So 2 pi times 0.310 times 10 to the negative 10 divided by 1 gives us an answer, which is 1.95 times 10 to the negative 10. Our next one, 2 pi times 0.310 times 10 to the negative 10 divided by 2. 9.74 times 10 to the negative 11, and then the last one for dividing by 3, we get 6.49 times 10 to the negative 11, but I'm pretty sure you can see how to do that. So the last thing that I want to talk about on this before we finish off is the evidence, because we've described wave-particle duality and seen that particles can have wave nature and waves can have particle nature, but what's the evidence for it? Because if a question is going to ask you about this, it'll ask for the evidence. So here's a summary of the evidence that supports both of these, and so requires the concept that light is both. So Young's experiment, then you've got diffraction and interference. Note, Young's experiment would be both with light and with the electron. And then for particle evidence, we have our black body radiation, our photoelectric effect, and atomic spectra. The four that I've underlined here, these are the actual experiments, while the diffraction and the interference is more an observation of what was happening and less of a rigorous experiment there, though interference is obviously part of Young's experiment because it was the whole seeing an interference pattern was what concluded that light was indeed a wave. So if you're going to be asked a summary about wave versus particle evidence, these are the things that I would recall, these four that are underlined, just to show, yep, here's the information. So in this video, we have learnt about the following. We have described wave-particle duality. We've calculated the momentum of light and the wavelength of particles, and we've identified our evidence for wave-particle duality. For your entrance slip to class, please complete questions 1 to 9 in chapter 12.3 Check Your Learning PDF. Copy your answers for this into the 4.2.13 space on eLearn. Thanks for listening, guys. Have a great one. Bye.